Okay, so for part B, let's just start by putting in the order. So since I was informed earlier that it's lowest to greatest, which one has the lowest boiling point? Yeah, F2 will have the lowest, and then what is the one right after that? Yeah, Cl2, and then you guys kind of get the point, right?
With like amounts matter.
What do you mean?
Like since F2 and Cl2, like there's two.
No, it doesn't matter. Because what was the reasoning behind it? I'll get to that in a sec. But what was the reasoning? Why is F2 the lowest? Yeah, exactly. So since F2 is the smallest, it's going to be affected by dispersion forces the least because there's fewer electrons moving around. And so same principle, it is less polarizable. Okay, so yeah.
F2, I think like one CL.
Like FCl?
Yeah. Or no, F2 CL.
F2.
Well, so you have F2 and then a different one is CL, which one would be?
F2 would still have the lower boiling point. Yeah. So you're talking about like, let's say we got rid of these two, right?
Yeah.
Yeah, it would still go in the same order. Cl2 is bigger, so it's more polarizable.
Oh, what if it was just CL instead of CL?
CL? You wouldn't be comparing them then. Yeah. Mm-hmm. Yeah, they're gonna be pretty reasonable with the comparison that you want to make. Yeah. Good question though. Okay. And then same thing, you would just write F2 is the least polarizable because least electrons. And then you can kind of go on from there. Since it has the least amount of electrons, it'll be affected by London dispersion forces the least, so lowest boiling point. Yeah. That's gonna be a little different because those we're talking about metals. So the properties are gonna be a little different. We're gonna be talking most about covalent compounds here. Yeah.
It's like just better show electrons.
Yeah. Okay. Yeah. Oh, okay, I get your question. Yeah, just look at the number of electrons, the size. Yeah. Okay. Let us move on to the next IMF. The next type of intermolecular force is called dipole-dipole. Okay, kind of a funny name. Dipole-dipole. It's like they're trying to say dipole-dipole. Oh. Yeah, I get very sad when I hear this phrase. You guys might like it. Yeah, they're telling me to die. Miles killed me? When Susanna gave me dysentery. Okay, so dipole-dipole forces are a little bit different than London dispersion, but it's the same principle, okay? Now, in London dispersion forces, we were talking about neutral compounds, right? Like F2 is neutral, Cl2 is neutral, neon, argon, they're all neutral. But in dipole-dipole, same thing, they're neutral, but here we have permanent dipole. So in London dispersion, it's an instantaneous dipole, okay? We're talking about instantaneous dipoles in London dispersion. Okay, it's instantaneous dipoles, right? When the electrons go to one side for a moment, they can go to the other side the other moment. But in dipole-dipole, we're talking about compounds that have a permanent polarity. Remember, we talked about depending on the electronegativity difference, one side will be more negative, one side will be more positive. That's a permanent polarity, and that's what contributes to dipole-dipole forces, okay? So the key thing to remember here is that dipole-dipole works with permanent dipoles, okay?
What is dipole?
Dipole is just saying that one side is partially positive, one side is partially negative, yeah. Yeah, so polar compound. So good example that's easy to think about that we talked about before is HF, right? We said that the side with the F on it will be permanently more negative, right? There's a dipole moment, which means that one side is partially negative, one side is partially positive. And so if we have multiple HF molecules next to each other, they will be affected by each other with a dipole-dipole force, okay? That's what that is.
So how would you word that if they say they have a dipole system? or moment?
Dipole moment, yeah,
They have it,
Yeah.
or-
yeah. Mhm.
So both equal atoms and ions be either of these.
Ion is different, yeah.
So these are all talking about.
Neutral, yeah. Yeah, it's a good point. If you want to mention that, this is talking about neutral. London dispersion is also talking about neutral things. Yeah, great point. Thank you. Okay, so again, you guys can probably figure out this pattern, but or this this reasoning. But the more polar something is, right? The more polar the molecule is, the stronger the dipole force will be. Okay. And the stronger the dipole force, the harder it will be to break them apart from one another. Okay. Okay, so let me ask you guys a quick question, pop quiz, before we do 9.28. Which one do you think will have a lower boiling point? Okay, HF or HCl?
HF.
Okay, who thinks HF has a lower boiling point? Yeah, I'll give you guys a second to think. So think about it. Who has a lower boiling? You can put your hands down for now. Okay, lower boiling point. HF versus HCl. Okay, so think about that for a second. You guys don't need to put your hands up, but we'll talk about it. Okay. Okay. So lower boiling point means, is there gonna be more dipole or less dipole? Yeah, less dipole. Okay, so I'm just gonna write dipole. Okay, less dipole forces, right? If there are less dipole forces, does that mean the molecule is more polar or less polar? Less polar, okay? Okay, because the polarity is gonna affect how much dipole moment there is, okay? So let's compare these two molecules, okay? So we got H on one side, so that's kind of our control, right? It's gonna be same on one side. Now, which one is more electronegative, fluorine or chlorine? Yeah, F is more electronegative, which means HF is going to be more polar than HCl, okay? So if HF is more polar, okay, that means the negative side, the partial negative will be a lot stronger than the partial negative on the chlorine. Okay, so if it's more polar, this acts more as a negative than this one does. And so that means HF is going to have more dipole forces with other HF molecules. Okay, which means that HF will have the higher boiling point and HCl will have the lower boiling point because it's less polar than HF is. Okay, yeah.
Yeah, like what were you thinking of?
Yeah, so these factors all come into consideration, but now I'm gonna mention this in a sec, but there's actually an order to the strength of these intermolecular forces. Okay, some are more powerful and it matter more than other ones. Yeah, so even more than distance is this positive, the partial positive and the partial negative. Yeah. Alrighty. So with that concept out of the way, I'm gonna give you guys some time to try 9.28. Okay, give you guys about 2 minutes to try. You got to write an explanation, so good practice for your exam, because hint there's gonna be a lot of explaining to do on this upcoming exam. Okay, so acetonitrile and propane, and I gave you guys the chemical formulas for that. Okay, they have similar molar masses. Okay, but acetonitrile has a boiling point of 355. While propane's boiling point is only 231. Okay, well, how can this be? How can they have the same or very similar molar masses, but such a big difference in their boiling point? Okay, so I'll give you guys about 2-3 minutes to talk about the person next to you, see if you can write an APFRQ style answer, and then we'll go over it together, okay? Okay, the hint that I gave you for this problem is you might want to draw it. That way you can kind of visualize what the structure looks like, okay? So let's look at acetonitrile. So I have the formula for you right there. Now, acetonitrile is gonna look something like this. You're gonna have CH3 on one side. You're gonna have a C and a triple bond to the nitrogen. Okay, that's acetonitrile. Okay, propane on the other hand is gonna look something like this. Okay, you're gonna have CH3, CH2, and then CH3. Okay. So that's what the structures of these compounds are gonna look like. Now, you're gonna notice that on acetonitrile, let's just kind of look at them. What's the most electronegative atom inside this molecule? N, right? So that means that you are going to have a dipole moment going towards the nitrogen side of that molecule. So there's going to be a permanent polar negative on this side, or partial negative, sorry, and a permanent partial positive on this side. Okay. Okay, so this guy is polar. Okay, but if you take a look at propane, do you guys see a dipole moment here? Is there one side that's more polar than the other? No, right? It's kind of just H around the whole compound. And so this compound right here is actually non-polar. No, it's magical, right? Now, what that tells us is that if you have a bunch of acetonitriles next to one another, there's going to be these partial positives and partial negatives, and they're going to line up together in order to kind of have this intermolecular force, this dipole-dipole moment or dipole-dipole force keeping them together. So in order to boil acetonitrile, you need to break all of the dipole-dipole forces between them. Okay, on the other hand, propane, there's no partial positive, partial negative keeping them together. Okay, so that's why acetonitrile has a higher boiling point. Okay, now, so let's kind of put some, I'm going to add a little bit of new information for you guys. So if you take a look at acetonitrile, acetonitrile has these intermolecular forces working inside of them. Okay, the first intermolecular force we talked about was dipole-dipole. Okay, it also has London dispersion forces. Okay, basically every compound has some sort of London dispersion forces. It might be very weak, but it has some. Okay, on the other hand, propane only has London dispersion forces. Okay, so dipole-dipole is actually stronger than London dispersion. So if you have a compound that has dipole-dipole compared to one that just has London dispersion, this one is going to have more IMF with one another. Okay. All right, so if we wrote that as a FRQ style answer, okay, you could write that, oops, acetonitrile has a dipole movement or moment because nitrogen is more electronegative than the other atoms in the molecule. Okay, therefore it has a permanent dipole moment, and and then you can write as a permanent dipole movement and is affected by dipole-dipole forces. Okay, so that will be the part about acetonitrile. You're kind of setting up that this one has dipole-dipole forces. And then you can write something like propane, on the other hand, is nonpolar and only has London dispersion forces, which is weaker than dipole-dipole. Okay, and then the last paragraph, you can write something like, therefore, takes more energy to break apart a sample of acetonitrile, increasing the boiling point. Something like that. If you can write it more concisely than me, I will love you more, but it's okay if you get it really long. Okay, I don't mind reading long explanations. If it's a story and you got to write on the back, now I'm taking off points. I'm not even going to read that. Yeah. She said something like, if Mr. O hits you with a truck, you turn into an anion. Something like that.
I remember you giving that exact story.
Yeah.
about like, it was about electronic rigidity.
Yes, something like that.
Like what, yeah.
Oh yeah, yeah. Is what is it? What's the relationship between the ionization energy for fluoride and the electron affinity for a neutral fluorine? Something like it was the last problem.
I like.
Obviously.
Yeah, only one person got a perfect on that.
Oh, cool.
I don't remember.
It was me, obviously, right?
That's not you. Yes. No, it's not an hour. It's a little shorter. It's like 40 minutes.
Thursday? So then we can have a Thanksgiving party.
Oh my gosh, Thanksgiving party.
What's our, I hate to like, what's our next unit after this?
I don't know. Kinetics? I think it's
Yeah.
kinetic. Oh, I hate kinetics.
Isn't that just physics?
No. You'll see.
No.
Okay. Everyone good with dipole dipole? Alrighty. Let's go to the next strongest one. So we're kind of going in order. So the weakest was London dispersion. Now we're on dipole dipole, and we're gonna go to an even stronger one. Now, this stronger one is technically a dipole dipole, but it's like the super version of a dipole dipole, okay? And it's called hydrogen bonding. Okay, hydrogen bonding. It is the blood pressure. Okay, so hydrogen bonding is a special type of intermolecular force. Like I said, it's dipole dipole, but it's a super strong version of dipole dipole, okay? So let's just take a look at this HF example right here, okay? So HF, AF is going to take the electrons from hydrogen, right? And if we look at the periodic table, hydrogen is very, very small, right? And so if it's stripped of most of its electrons, basically all it is, it's just a naked proton. So on one side, it's basically just a positive charge. Okay, it's more positive than other polar compounds where it's a partial positive. And then we have a partial negative on the other side. That's one way to think about it. Hydrogen is super duper small. It gets all its electrons taken. So it's kind of naked on that side. And so it's just pretty much positive, just a positive charge because it's a naked nucleus. Okay. Now, because of that, if hydrogen is bonded, right, a single bond or with a very polar atom, okay, so the ones you want to remember are HF, HO, and HN. So if you have a molecule where hydrogen is bonded to F, N, or O, okay, it's going to create a hydrogen bond. And this is what it looks like, okay? So this naked hydrogen right here is going to feel a hydrogen bond between the partial negative of this water molecule, the oxygen, because this hydrogen is super duper exposed. It's just a nucleus basically on that one side, okay? So it's going to connect very strongly with the oxygen on another water molecule. Okay, and same thing with all these other examples. HF, this other hydrogen is going to feel a hydrogen bond between itself and F. Same thing here with ammonia. Nitrogen and hydrogen will have a hydrogen bond, and then so on and so forth. It could be between different compounds like this. Hydrogen bond and hydrogen bond. Yes.
Do you draw the
Dot, dot, dot.
like no the lone pairs before the hydrogen dots, like to show that it's taking the
You don't have to. It's kind of implied that there's gonna be lone pairs. Yeah, but you don't have to.
How would the hydrogen bond occur between like nitrogen bond one when oxygen is more electronegative?
Yeah, so it doesn't matter because so you're not going to compare the nitrogen and the oxygen because the electronegativity only matters within the atom for so if we take a look at this, right? All the electrons are going to get pushed in the ammonia molecule.
Yeah.
It's going to get taken by the nitrogen, right?
Yeah.
And in the water molecule, the oxygen is going to take all of them, right?
Yeah.
So it doesn't matter that oxygen is more electronegative than nitrogen because it's going to rotate so that the nitrogen is going to rotate the water molecule so that it can form a hydrogen bond with the hydrogen, with hydrogen bond with the hydrogen. Yeah. Yeah. So these two, since they're both very, they're gonna become negative because they're taking most of the electrons. They're not really gonna interact with one another. It's just gonna rotate. Yeah.
Is there like a specific one hydrogen over another?
No.
Or
Yeah.
Why? Okay.
Yeah. So, and we're talking about these. I mean, we're talking about them like individually right now, but if we had like a big sample of it, there's like multiple atoms, right? So this hydrogen is going to get eaten up by another, or hydrogen bond to another thing, which is going to, and this one's going to be to another thing. And so it just depends on the interactions. Yeah.
Are we gonna do skeletal structures like the spheres that?
No, we're not. Mm-hmm. It's more electron. Oh, why is the N attracted to the hydrogen? Because which one? Right here? Oh, like down here? Yeah, that's just an example to show that like it would look like this then, right? So this hydrogen right here will be partially positive, and from for a different ammonia molecule, this will be partial negative, so it'll form a hydrogen bond. Yeah. No, it's not going to take the electrons because it's a different molecule. Yeah, that's a good point. The other molecules are not going to take away electrons because then you would basically be breaking apart this structure, right? Yeah. 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 So yeah, keep that in mind. Covalent bonds are way, way stronger than any intermolecular forces. Okay. So this molecule, the stability of that matters more than the intermolecular forces. So we're not, it's like we're not even talking about the same thing there. Yeah. 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 It's not an actual bond, it's just attraction. Yeah. So it's like if you're in a relationship, you're bonded with someone else, right? But you can see someone that you think is objectively attractive, right? There's nothing wrong with that. You're not going to do anything. But anyway, is there really? I think we're lying to ourselves if we say that you don't find someone objectively attractive. Anyway, yeah. That would be a lie, exactly. Anyway, okay, so like I said, hydrogen bonds are just a special type of dipole, and it's because nitrogen, oxygen, fluorine are so electronegative, it creates a very big disparity in the polarity in the molecules, okay? Okay, so let's take a look at 9.29. Okay, basically all you're gonna do is look at these 4 compounds and tell me, do they have hydrogen bonds? Okay, very simple. Okay, so take a look at it. And if they don't have hydrogen bonds, I want you guys to tell me what intermolecular forces they are affected by. Okay, so go through each of these molecules and tell me, do they have London dispersion? Do they have dipole-dipole? And do they have hydrogen bonding? Okay, so try that and then we'll go over in about 3 minutes. Okay, so let's take a look at these compounds. Let's go by IMF because we're learning about the order of the strength, right? So London dispersion forces, they all have London dispersion forces, right? So methane has London dispersion forces, hydrazine has London dispersion forces, methyl fluoride has London dispersion forces, and hydrogen sulfide has London dispersion forces, okay? Okay, let's talk about the next section now. The next strongest one that we learned are dipole-dipole, and we're gonna go through them and figure out if they have dipole-dipole. Okay, so let's start with methane. Does methane have dipole-dipole? No, because it is non-polar, right? So methane does not have any dipole-dipole. Okay, let's go to hydrazine. Does hydrazine have dipole-dipole? Yes, it does. And the reason why, and this one's kind of tricky, is because if we draw it, this is what hydrazine looks like, okay? It is gonna look something like this. And there's lone pairs on the nitrogen. And so you will have a dipole towards the side that has the lone pair electrons, yeah. No, because the inverse of that would be if you had something that looks like this. If you had, instead of 4 H's, let's say you had 6 H's, this one has more H's, right? But this one's non-polar because there's no side that has more electronegativity. So yeah, that wouldn't be the right reasoning. It's because of the lone pairs that nitrogen has. So whichever side has the lone pairs is going to be more electronegative. Yes, yeah.
Like that, would it put the H like on the bottom or the top? It would be like that, right?
It doesn't matter. Like you can put, I mean, if you really wanted to, you can.
The bottom and the top, and you put the lone pair electrons to the
Yep.
side to different.
Oh, okay, I see what you're saying.
Yeah.
Like this, right?
Yeah.
So yeah, that's a good point. But it actually would end up rotating to be polar because remember, it's not two-dimensional, right? It's three-dimensional. So if we wanted to really, get into the nitty-gritty, it would end up, one of them would end up going in, and then one of them would end up coming out, and they would rotate until one side has the polarity. So yeah, this one is polar.
Why was it the lone pairs?
Because remember, lone pairs are basically just raw electrons, right? So it's raw electric, like negative energy. And so there's nothing more negative than electrons. Yeah, electronegativity is one side has more electrons, but obviously if you have the electrons themselves, it'll be more negative on that side. Good question. So yes, partially positive. So yeah, hydrazine will have dipole. Okay. Let's go to CH3F. Will methyl fluoride have dipole?
Yes.
Yes, it will. It will have dipole. Because if we draw it, it will look like this. And so obviously fluorine is the most electronegative. So there will be a permanent dipole towards fluorine. Okay. All right, let's go to the last one. H2S. Will this have a dipole? Let's draw it. So we got sulfur in the middle, hydrogen's on the outside, bonded. Sulfur gives you 6 valence electrons, hydrogen gives you 2, total 8. So 2, 4, 6, 8. So is one side going to be more polar? Yes, it will. Because remember, three-dimensional. Yeah. So these will actually, basically the electrons will either, see these two, they look flat, but they'll either congregate in towards the page or out towards the page towards you. So there will be some kind of polar moment either towards you or away from you. So this one is also dipole. Okay, yeah. So you got to really start thinking about the three-dimensional shape now, because that's how we can see the dipole moment. It won't just go side to side. It can go in and out. Okay. All right. Last one. Let's go to hydrogen bonds. Okay, so let's start with hydrazine. Will hydrazine have hydrogen bonds?
Yeah.
Yes, it will. Okay, because we got lone pairs, right? The hydrogen is bonded to a nitrogen, so this is an extremely polar bond. And so it's going to be attracted to, it's going to have a it's going to have a hydrogen bond with the lone pairs on the nitrogen atom. Okay. And so again, look for nitrogen hydrogen bonds, or nitrogen oxygen fluorine hydrogen bonds, and that will tell you if it has an H bond or not. Okay, so hydrazine will have a hydrogen bond. Okay. So we can automatically kick this guy out, right? H2S does not have a hydrogen bond because there's no nitrogen, oxygen, and fluorine. Okay. And this is the one that could be a little bit tricky. Does CH3F have a hydrogen bond? Okay, I want you guys to think about it. Okay, let's look at the structure. Okay, remember, it has to be a hydrogen nitrogen, a hydrogen oxygen, or a hydrogen fluorine bond. Okay, obviously there's no oxygen and no nitrogen, so we can skip those. Okay, inside of methyl fluoride, is there a hydrogen fluorine bond? No, it's a carbon hydrogen bond, right? So this actually does not have a hydrogen bond because the hydrogen is bonded to carbon, not fluorine. So there is a dipole, but it's not a hydrogen bond. Yeah.
Is it because carbon,
Yeah, it's not super electronegative like those three. Yeah, it has to be a hydrogen bonded to one of these three. Okay. Yes. Yes, it has to be H bonded to F, H bonded to O, or H bonded to N. It doesn't matter what these guys are connected to. So like, for example, here we have an H bonded to a C bonded to an F. That doesn't count because the original bond is not between one of the three electronegative bonds. Yeah, so it can get a little bit tricky. Yes, just those three. Okay, so if you take a look at these compounds, which one do you guys think would have the highest boiling point? The hardest to boil? Yeah, hydrazine is the hardest to boil. Which one do you think has the lowest boiling point? CH4, exactly. You guys got it. Yeah. I agree. Please do, guys. It's hard grading when people get stuff wrong. I have to write stuff and think about it. I'm fail all of you. I'm gonna fail all of you. Okay. All right. So we are almost done. There is one more type of intermolecular force that we need to talk about. Okay. And this last intermolecular force is the strongest. And this is an ion dipole force. Okay, ion dipole. I know. Did I? Oh, my fault. Okay. Ion dipole. Okay, and ion dipole sounds exactly the way it sounds, or is exactly the way it sounds. It's where you got an ion, you got a positive or negatively charged particle, and it has a intermolecular force with a dipole. Okay, so for example, we got water. Salt water is the easiest one to think about. When you put a piece of salt in water, it breaks apart into sodium ion and it turns into a chloride ion. Okay, these are positive and negative. It's not partial, it just is positive and negative. But water, since one side is partially positive, partially negative, they're going to attract, depending on which side you're looking at, it's going to attract to the chloride. The positive hydrogens are going to attract to the negative chloride, and the partially negative oxygen is going to have an interaction with the positive sodium. Okay, and this is the strongest intermolecular force. Okay. Oh, the white is going to be the hydrogens, and the red is going to be oxygen, H2O. Yeah, sorry, I should have clarified that. Yes, exactly. Exactly. And then the water molecules basically attack the positive and negative ions. And this is how you dissolve salt. Yes. Hmm? What do you mean? This is why salt dissolves in water. Because the water molecules start taking it off the block of salt or whatever. Yeah. Yeah. And that's why if you, let's say you put a block of salt and a block of sugar inside of water, salt breaks down a lot faster and easier than sugar does. And it's because of the ion dipole forces. Yeah. I know, it's magical, isn't it? Yeah. All right. And so that's kind of it for the intermolecular forces. This is a little flow chart that you guys can use if it helps. If it doesn't help, don't use it. But this is a flow chart that you guys can use to compare IMFs. So the left side is the weakest, like we talked about, dispersion, London dispersion, then dipole, hydrogen bonding, ion dipole, and then these are ionic bonds, which they're not really IMFs, but it's there to show you that these are stronger. Okay. All right, so that's gonna be it for unit. What is this? 9
Out of
14, 15 units? Yeah. 14? Okay, 14.
yeah, but there's like something like
Yeah, they get stupid long after this.
like the acid
Like you will actually have some time between tests. Isn't that incredible, right? Okay, so we're gonna do a couple practice problems because like I said, this takes up a big portion of the AP test. I want to make sure that you guys are comfortable working with IMFs and comparing IMFs. Okay, so it's actually gonna get a little bit, I think these can get a little hard. Okay, so we'll start with the easy one. Okay, I'm gonna give you 4 basically, or 5 random compounds. Okay, you got BaCl2, H2, CO, HF, and Ne, neon. I want you guys to put them in order of increasing boiling point. Okay, you can do all of this by looking at their IMFs. So use the chart that we just looked at, use their notes, figure out what intermolecular forces they all have, and depending on what they have, that's going to be the strength of them being connected together. So I'll give you guys about 4 minutes to try this, and after that, we will go over it together. Yeah, let's go over it. Okay, so we are going to start by going over all of these compounds, and we're going to figure out what the strongest force inside of those compounds are, okay? We all know they all have London. We know that some of them might have dipole, but we're going to figure out the strongest in there, okay? So if you take a look at BaCl2, out of the forces that we talked about, what is the strongest force available for BaCl2? It's not dipole. It's not dispersion. BaCl2. BaCl2. Not hydrogen bond. Gonna go through all the examples. Okay, we said this one, this one, this one. Okay. You got two. Yeah, it's an ionic bond. If you guys take a look at it, BaCl2 is an ionic compound, right? Yeah, this is an ionic compound. Okay. Okay, and we know that just from what we learned before, right? If you got a metal and some non-metals, they form an ionic bond. Okay, let's take a look at H2. Okay, yes. Yeah, because BaCl2, it's made by Ba giving electrons to the Cls. That makes Ba 2 plus, Cls minus minus, and they make BaCl2. Yeah.
Oh, so it's like are ions.
Yeah, present. Yeah. Are there ions in the compound? Yeah. Yes. Yes. That one was kind of a trick question. Yeah. If that's the one you got wrong, then don't worry about it. You're on the right track. Yeah. You guys know me. I like to throw little curveballs at you. Okay, let's go to H2. What is the strongest IMF that H2 experiences? Yeah, it's London dispersion.
Yep.
Okay. Okay, because London dispersion forces. Because H2, okay, there's no dipole, right? It's non-polar. It's the same on both sides. No hydrogen bonding. It's just hydrogen. There's no ions in there. It's just H. Okay, this is the most boring compound. Actually, it's not true. It blows up. Okay, CO. Okay, what kind of what is it? Intermolecular forces does CO experience? Okay, it does experience London. Does it experience dipole? A little bit, right? Carbon and oxygen, there's a little bit of electronegativity difference. So yeah, there's going to be a dipole force. That is the strongest that it experiences. But if I'm just being straight with you, it'll be very small. Okay, so we'll write Lil.
That's what I did too.
You wrote Lil? Nice. Yeah, it does experience a Lil dipole. Okay. Okay, let's go to HF. So if you take a look at HF, what is the strongest IMF that this guy will experience? Yeah, H bond. Yeah, H bomb. H bond. Good. All right, and then last one, neon is just a singular atom. So what does neon experience the strongest? Not ion. Neon is a noble gas. It's inert. Yeah, London dispersion. Okay, because it's just neon by itself. Okay, so we want to put them in terms of increasing boiling point. So let's figure out which one has the lowest boiling point. Now our two options are H2 and neon, right? Because they experience the weakest intermolecular forces. But which one do you think is the weakest out of the two? Yeah, it's H2. Why is it H2? Yeah, it's smaller, right? It's just 2 protons, 2 electrons. Molar mass is 2. So that one's gonna be smaller, and the next one right after that is going to be neon. So we're gonna cross that out. Yeah, it's the smallest. Yeah. Okay, so these two will experience London dispersion forces. And that's why they have the lowest boiling point, because that's the weakest intermolecular force. Okay. Okay, which one is next? Yeah, we got CO, okay, carbon monoxide, and it's because it experiences, like Vivian said, a little dipole. Okay, just a little. We're gonna cross that out. Okay, now we got two compounds left. One of them is a hydrogen bond. So which one is the next one? Yeah, HF, and it's because it has an H bond. And then, which means obviously the last one is going to be BaCl2, which is going to be an ionic bond. Okay. Okay, now you guys might have been a little bit confused. Why is an ionic bond considered intermolecular force? It's just in the molecule itself, right? And it kind of has to do with what we were talking about water. Remember how it's made out of individual ions, right? So if you got a BaCl2, it's basically something like this. So there's no covalent bond. They're bonded together because one of them is positive and one of them is negative, right? So if you have a chunk of BaCl2, what actually happens is it's made up of some kind of this crystal-like structure where where the positives and the ions have bonds with one another. Yeah, go ahead. Yeah, a lattice structure. Wow, great word. Hey, Vivian, when I retire, you can take my spot, okay? You have a future in this, okay? So yeah, it's gonna form a lattice structure, which is also why, if you guys remember, ionic compounds have very high boiling points. It's extremely hard to boil them, right? Have you ever tried boiling salt? It's not going to happen, right? It takes way too much energy to break those intermolecular forces. That's why ionic compounds are going to have the strongest IMFs, okay? Isn't this fun, guys? Just ordering 5 things together.
We're gonna do any labs, more labs?
We will have labs coming up. I think we have one before Christmas break. Yeah, I know. Breaking up. Hey, you know the Asian policy, right? You break it, you buy it. All right. Let's skip this one. We'll do one more and then we'll be done for the day. Sound good? Okay. Let's go to the handout that I told you to look at. So these are good practice problems for the exam. I will post the answer key after we're done with class. Because I was told that you need the answers. Check your answers. Okay. Okay. Some person in this class. Okay. Let's take a look at this one right here. Okay. Let's look at 9. Okay. So let's see if you guys can finish the whole thing on your own. Number 9. Okay. So I'll give you guys about, what time is it? 5 minutes. And then after that, we'll go over the answers and then we'll be done for the day. Okay. Okay, so let's start with 9A. Okay. Okay, so we want to figure out which one of these 3 has the lowest vapor pressure. Now, before we get into that, let's talk about what vapor pressure is. Vapor pressure is when you have some kind of liquid. Okay, the molecules inside of that liquid, they automatically turn into vapor. Okay. Okay. This is just kind of a reality. Molecules in a liquid turn into vapor. It doesn't have to boil, just automatically vaporize. So let's look at Cl2, let's look at Br2, and let's look at I2. We want to figure out which one of these basically vaporizes the least, okay? So if something has the lowest vapor pressure, does that mean it breaks apart easily or it's hard to break apart? Yeah, it's hard to break. Okay. Okay, and the reason why is because if it breaks very easily, it's gonna vaporize a lot, right? Most of the or a lot of the molecules are just gonna go flying up and vaporize automatically. Okay. Now, out of the 3, let's figure out the intermolecular forces. So these 3, what's the intermolecular force that they all experience? Yeah, London dispersion. Okay, are there any other intermolecular forces that they experience? No, there's no hydrogen. There's no ion. There's nothing else. It's just London dispersion, right? Because the other one is dipole-dipole, but none of these are polar, right? They're both same element on both sides. So the only IMF they experience is London dispersion. Okay, so basically we want to figure out which one has the most London dispersion, because whichever one has the strongest London dispersion is going to break apart the least. Okay, so which one of these three has the least, or the most, sorry, the most London dispersion forces? Yeah, I2. So I2 is going to be the compound with the least vapor pressure because it has the most London dispersion, which means it's going to stay together in liquid form and it's not going to vaporize. If it doesn't vaporize, there is less pressure compared to these guys. These guys will have way more pressure because they will break apart more. Okay, and granted, they're at the same temperature. That's a pretty important condition.
Bigger.
Yes, it's bigger. It's a big one, big boy. Okay. All right, makes sense. Part A, that's probably one of the harder ones just because vapor pressure. Okay, let's go to highest boiling point for part B. Okay, so for part B, we got HBr, Kr, and Cl2. Okay, so we want to figure out the intermolecular forces that they experience. So let's start with the lowest one, or actually, yeah, let's start with HBr. What is the strongest intermolecular force HBr experiences? Yeah, dipole. Okay. What about krypton? What is the strongest IMF that experiences? Yeah, London dispersion. And then Cl2, what is the strongest one that this experiences? Yeah, dipole. Oh, sorry, my bad. Sorry, dipole. I'm sorry, London dispersion. I said dipole again. It's just too fun to say. Dipole. Okay, London dispersion. Yeah, dipole. Okay, so out of three, very easy. Which one is the hardest to break apart? Yeah, the dipole one, which is HBr. So HBr will have the highest boiling point. Okay, let's go on to the next one. We got lowest vapor pressure. Okay, so this one basically same thing, lowest vapor pressure. So low vapor pressure means that it is hard to break. Basically, it means there's stronger IMFs. Okay, so stronger IMF. Okay, so this one can get a little bit complicated just because of the way how big the structures are. But we can visualize them like this. Okay, so the first compound is just CH3, CH2, and CH3. Okay, the next one is CH3. There's a C, there's an O, there's a CH3, and the last one is CH3. Oh, sorry, CO, CH3, CH2, CH2OH. Okay, so let's start with the first one. Let's just look at this. Is this polar or non-polar? Non-polar, which means the strongest IMF that this experiences is, yeah, LDF. Okay, yeah, not LDS. That's Latter-day Saints. Okay. All right, let's go to this one right here. Is this one polar? Yes, this one is polar because of the oxygen right here. Okay, so this one's polar. So there's going to be some dipole. Okay, let's look at this one right here. Is this guy polar or not polar? Yeah, it is polar. What's the strongest IMF that this guy feels? Yeah, H bonding. Good catch. Okay, because of the, I kind of try to hide it right there, but oxygen-hydrogen bond. And so this is actually going to have an intermolecular force with the hydrogen from another one of these. Okay, so CH2, CH2, CH3. So they're going to have hydrogen bonding. So which one experiences the most intermolecular forces?
The last one.
Yeah, the last one right here. It's called propanol. Okay, propanol. Yeah.
the vaporization, like versus like the pressure.
Yes. Yes. Okay, and then last one, yes. Uh-huh. Uh-huh.
Sorry to go back.
No, you're good.
If you're trying to decide, like, between AR and CO2, like, that's higher.
Uh-huh. Then you would have to look at the size of the molecules, which gets very different or difficult because one has two is diatomic, one is monatomic. They're not going to ask you to compare a monatomic and a diatomic like that. If they share the same types of intermolecular forces, yeah. Good question. Yeah, that's beyond the scope of this class. Okay, last one. I am going to give you guys, I'm just going to give you guys the answer. It's going to be this guy right here. Okay, largest heat of vaporization, because this means that you need to put a lot of energy in order to break the bonds. It's basically going to be the one with the most IMF. Okay. Alrighty, guys, that is pretty much it. You guys got